Well, it's already past the hour, so Vern Slater is with Active Treatment Systems, Inc. And we have had a long relationship with ATS, Inc., doing education events for years now, both on Stormwater Awareness Week and also in our QSP, QSD classes and other events. Vern is very knowledgeable when it comes to active treatment systems. So you want to make sure that you give him any of the questions that you have about them. He's very knowledgeable about what the construction general permit requires, about the chemicals and that are used and the processes that are involved and required by the permit. So Vern, why don't you tell everybody a little bit about yourself, and let's go ahead and jump into our workshop.
Okay, I'm Vernon Slater. I got 15 years of experience in the active treatment system world. My qualifications, I've earned a CPAS, QSP, QSD, QIS certification, and then I'm also an active treatment system trainer. Position in the stormwater community is essentially a project scientist for active treatment systems and the design and setup of those systems. So this presentation is going to proceed where I've organized the questions that I've received over the last year and last year also in sections where information is similar. I'm going to start with more of the entry-level stuff first and then move on to more in-depth information and system sizing, basin design recommendations, and jar and dose determination and testing. There's a live experiment, so hang with me. We'll get this done. And now I need to share screen. And now I've got this in my way here. Let's me minimize this if I can. All right, so the first question I received that was new this year was, what are the requirements I must follow when operating an active treatment system? Attachment F of the general construction permit gives you all your rules. It is your Bible to active treatment systems. This is last permits front page. This is a 10-page document. Right up front here, it says we got to discharge at 10 NTU on a daily weighted flow average, no more than 20 NTU on a single sample. Now, the new permit has these same numbers in place, but it also adds in pH from 6.0 to 9.0. And notice here, dischargers are choosing to implement active treatment system on their site shall comply with all the requirements of this attachment. Again, your Bible. So how do I become an operator? In the old permit, you had to go through a formal class with a certificate and requirements for testing and certificate renewal. In the new permit, they've removed education. I do not believe you can take somebody and throw them at one of these systems without at least giving them the 8-hour class and 32 hours of somebody operating with them, teaching the basics in the field. So the new permit, it's not called out, but I wouldn't get out there and do these things without having some kind of training under my belt. So last year's question, why is there a need for an active treatment system? I never had to have one before. I still hear these. And one of the big pictures I have right here is this. This is a perfect picture of what went wrong with traditional BMPs not having an active treatment system on site. And so some facts from this: 1/8 of an inch of soil from 1 acre is about 25 tons of sediment deposited into the local lakes, rivers, and oceans. Excessive turbidity or suspended solids absorb more energy, raising the water temperatures. And the prediction is by the year 2200, the current models show all ocean ecosystems will have been changed by temperature increases, and many fish populations will not survive unless we do something now. Large amounts of suspended solids or clays may clog the gills of fish and kill them directly. Excess turbidity may bury and kill eggs laid in the bottom of lakes and streams. High turbidity blocks out light penetration that other beneficial plants and organisms need to grow. High turbidity promotes algae growth, and as the algae dies off, dissolved oxygen is consumed in the decomposition process, causing fish kills. Turbidity negatively affects aesthetic qualities for recreational uses. And what about municipalities? Treating high turbid water negatively impacts their systems. And so now we look at this picture, and the water is running off this site very fast into the street. And then you end up with pictures like this, where it's running into the storm drain, and out of the storm drain right to the local stream. ATS Y, this shows why. You look at this turbid water and this clean water, this took 5 minutes. Here's another one, no treatment with treatment. And then you got guys like this that are not very happy from the turbid water they're in, and fish like this that may not survive very long in these kind of conditions. And then we have to start thinking about what about the regulations or environmental groups and fines from the general construction permit can be for large discharges, $1 to $2 a gallon. And that can add up fast when a large discharge can be 1 million gallons. So the next question, what is turbidity and why does turbid water remain dirty over extended periods of time? Turbidity is a general term used to describe the cloudiness or dirtiness of water sample. The turbidity of a given sample is determined by passing a light through a sample, measuring the reflective or scattered light in that sample. It is measured using a turbidimeter like the Hawk 2100Q, the Hawk 2100P, the Microtol 2 turbidimeter inline. Any of those turbidimeters can measure this. The measurement unit is a nephelometric turbidity unit, or just NTU. The higher the NTU, the dirtier the water. Turbidity is a good measurement of a water body's health. And the turbidity range for construction discharge, 250 NTU with traditional BMPs. Or if you're going to have an active treatment system, then that drops to 10 NTU average and 20 NTU max. And turbid water remains dirty over extended periods of time because of 2 factors. The primary mechanism involved with the remaining water remaining turbid is the electromagnetic repulsion of each fine suspended particle. These particles are generally smaller than 0.2 millimeters, and they are anionic in charge. These negative charges repel one another and do not allow particles to conglomerate into larger settlable solids. The secondary mechanism is turbid water is generally made up of very small 0.2 millimeter or smaller particles, and they remain suspended due to their small size. Without some type of encouragement to bring these particles together, settling times can be from days to years.
Hey, Vern, we have a request. Could you center your PDF
All right.
just a little bit, or zoom in a little bit?
Hold on.
There we go. Perfect.
Is that a little better?
Yeah, maybe zoom in just a bit.
All right.
Just hit, yeah, that's great.
And then let me bring this back center.
Wonderful. Thank you.
All right. Let's see, where was I? Okay, so the next question. What is pH and what does it have to do with stormwater treatment? pH is a measure of a water sample's acidity or basicity. The pH scale is 0 to 14, where 7 is neutral. Values below 7 represent acidic conditions, that would be these. And values above 7 represent basic conditions, and that would be these. Different treatment technologies may require different pH ranges for effective contaminant removal. For example, a popular coagulant used in treating construction stormwater runoff is a product known as Kitazan acetate. Effective pH range for this polymer is lower than pH 9 and above pH 5. At a pH of 10, the polymer just will not work. And then to raise a low condition, we've got, measurements in here. We could use sodium bicarbonate or more industrial chemicals like sodium hydroxide. But when you start using these industrial chemicals, you got to start thinking about cost, handling, and how they're going to be injected so you don't end up injuring somebody or yourselves. On the other end of that scale, we have the high end. We want to bring that down. We use carbon dioxide or dry ice. Stronger chemicals like hydrochloric acid could be used, but you have the same issues with finding out costs, handling, and how you're going to inject it into the system. So what is an active treatment system? Any treatment system that uses a chemical to reduce fine suspended solids from construction site stormwater discharges. The typical system is a collection of plumbing, pipes, pumps, filters, tanks, basins, coagulants, flocculants, instrumentation with automatic water quality recording capabilities. And this is a worded diagram of what's going on from all the way from collecting, coagulation, flocculation, settling in a storage tank, main polishing with a little bit of chemical here, filtration, monitoring, and then off to discharge. This is a drawing of one of these systems where the influent comes into this big pond. It comes out of the big pond, it comes over here for an injection, goes into the small pond, comes out of the small pond, gets a small bit of Kitazan added to it. And if it's in spec, it gets to go ahead and run around here to the filters, come out of the filters. And if it's still in spec, it gets to go to discharge. An active treatment system protect natural waterways from the negative consequences of construction, land disturbances, or other man-made water quality problems. The active treatment system is the BMP of last resort, used when traditional BMPs may not control the accelerated release of sediment from erosion caused during rain events, and used where highly erosive soils are present, long steep slopes, clay or colloidal clays are present, and on large sites where the sheer volume of water capture cannot be released without violating numeric action limits or numeric effluent limitations. What is the difference? This is a picture of the system. We got our tanks, our hoses, pumps behind the control unit, a control unit and filtration system. Here we have the filtration settling control unit with the filters inside and a power unit. The pumps cannot be seen in this picture. So what is the difference between an active treatment system and a dewatering system? An active treatment system uses chemical reactions to remove contaminants from water. Active treatment systems must meet chemical residual requirements in the discharge, and the active treatment system will always use chemicals in the treatment process. Dewatering systems are generally systems designed to remove contaminants by way of mechanical means. These systems differ from active treatment systems in that they will use settling, mechanical filtration, and specialty medias in place of chemicals. However, at times, the turbidity level of the water flowing to the dewatering system may need removal before specialty media or to meet local discharge requirements. In that case, the dewater system will become active in the fact that chemicals will be applied to reduce suspended solids. In this case, residual requirements will need to be met. Effluent monitoring requirements change with dewatering systems. Typically, the dewatering system will run in recirculation, then sample to see that discharge requirements are met. After verification, the system will then be monitored on a periodic schedule developed for that discharge location. Could be a week, once a month, once every 2 weeks, once every few days. It just varies depending on the dewatering system. So, how does an active treatment system clean and correct pH of construction stormwater runoff? Active treatment systems use chemical, sedimentation, and filtration to correct turbid construction stormwater runoff. Turbidity is removed using cationic polymers. So what we've put in here is some cationic polymers. They start grabbing these negative charged particles of soil, bringing these together, and starts the coagulation process. After the settling period, the cleaner settled water is sent to filtration turbidity is removed because the chemicals bind with anionic suspended solids, causing them to combine into larger masses, settle out. Okay, and then after the settling period, the cleaner settled water is sent to filtration, where the long chain polymers with the attached particles can easily be filtered out. After some operational time, the trapped particulate will begin to clog the sand filter and backwashing will become necessary. This process reverses flow through the filter and out separate plumbing back into the headworks or into a designated backwash tank. So the next step.
Vern, we have a question that I'd like to go ahead and field to you. Someone asked, is the ATS generally effective for CIDH projects that use high molecular weight drilling fluid, not just grout and high pH?
It can be used. We have done these successfully in the past. Sometimes they need specialty medias depending on the materials that are coming into contact with the ATS system. So these can be used for that, and sometimes not so well.
All right, thank you.
In more detail, the dirty water is collected where some of the heavy settle out in sand and gravel. This water is then bench tested to find the best starting dose. With the dose known, the raw water is pre-treated using a static mixer for a flash mix. This step is followed by about 30 seconds of secondary mixing as the water flows through the plumbing and into the tank or basin. Now that pre-treated water flows through a tank or basin for about 90 minutes. So here's our static mixers, a couple of different types. Now the pre-treated water flows through a tank or basin for about 90 minutes of contact time. And the you'll see that we have an underwear here that forces particulate down to the bottom and allows the clean water to rise to the top to come over the overwear onto the other side and then off to filtration. In a typical one season small system sites, 200 to 800 gallons per minute or less, treatment will usually be done in tanks. As water flows through the tank, it will pass by underwears and then into overwear. In basins, basin design is the most important. You're going to need 90 minutes of contact time as a design feature that will need to be met. And with designing a basin, perfectly round basins are not the best design for footprint use. Short-circuiting the pond can occur. Therefore, oblong, rectangular, and divided ponds are highly recommended. So we've got our oblong, our rectangular basin, our round basin with a weir wall. But avoid this. You put just a round hole, pump water in, take water out. It shoots through the center of this pond, not using any of the water out here on the edges to settle. That makes treatment much, much, much harder. So then water is then pumped from the overwear side or opposite end of the pond, usually at 100 NTU water clarity. The water is then filtered and sent to discharge. Certain California Regional Water Board requirements must be met before discharge, including discharge turbidity requirements, pH requirements, automatic logging of water quality parameters, training requirements, and chemical residual requirements. pH correction is corrected using 3 methods. So we'll sparge gas into the waste stream or through an injection quill and a static mixer. We can add pH correction chemical to the tanks by hand using sodium bicarb or dry ice, or chemical injection into a static mixer. What types of equipment are used in active treatment systems? Filters, pumps, tanks or basins, valves, chemical metering pumps, compressors, tanks or basins. And notice these basins right off the top, oblong in shape. Auto valves, automatic fail-safe open, fail-safe closed. Manual throttle valves are what these are instead of automatic. Instrumentation, there's your turbidimeters, pH meters, flow meter, and the filter. These are types of equipment used in the system. So I get asked a lot, is how big of an area is this going to take? What are the system footprint requirements? So a 200 gallon per minute system, something like this, is going to take up about 800 square feet of space. The shape of the pad will be based on site constraints, but we'll need to have room for a tank 40 feet long and 10 feet wide. For each additional 200 gallons per minute added, add another tank, you're going to need about 400 more square feet. And then once again, add another tank, add another 400 square feet to your pad. And for the final tank at an 800 gallons per minute, you're going to need to have, now every once in a while, you can squeak out using tanks 1,000 gallons per minute. That will work. But when it starts getting over 1,000 gallons per minute, or as multi-year operations, basins rather than tanks start to make more sense. So how is system size decided? System size is determined by looking at the overall project disturbed acreage and the rainfall that will occur on that site in the 10-year, 24-hour rain event. So with the amount of rainfall known, available storage must be calculated. Then the system size is calculated to pump and store the volume equal to the 10-year, 24-hour rain events in 72 hours. This yields the minimum system size for California water boards will approve. However, backwash and equipment or system upsets must also be considered. Therefore, a recommended system size calculation would be 35-hour pump down. Disturbed acreage is found in the notice of intent, and I have a copy of the notice intent here. This is talking about the latitude and longitude, which gives you location, area exposed to stormwater, 260 acres, and it talks about a lot of information is given here. And then you got to go to the rainfall, which you find on NOAA's Atlas 14-point precipitation frequency estimates. You pump in the latitude and longitude, you get a location, and then you get this handy chart that shows duration 1, 2, 5, and 10 year or more. And then the hours, 5 minutes, 10 minutes, all the way down here to 24 hours. So the 10-year, 24-hour rain event yields of 3.88 inches. So as an example, let's assume this is a 10-acre site. We have 3.88 inches of water, 10 acres times this many gallons per acre per inch yields a total of 1,053,575 gallons. If we divide by 72 hours, divide by 60 minutes, we get a 244 gallon per minute system without backflush or considering any potential upsets. So at 35 hours, the system size is 462 gallons per minute. It's just divided by 35 hours instead of 72. And then that will account for backflush and potential problems along the way. So what is Kitazan acetate? Kitazan acetate is a non-toxic cationic biopolymer. It is made from chitin found naturally in crab shells. Its unique characteristics attract and bind with anionic solids and colloidal particles. Kitazan polymer starts at a pH of 4 and in tightly wound molecules with all their cationic sites all hidden, for lack of better words. This is a 2-dimension diagram of a 3-dimension, so it's not the best looking, but it does give a representation. As the pH rises, the long chain unfolds into a chain with many cationic sites that can now interact with and bind anionic particles of suspended solids. So at a pH of 5 or more, you start seeing the chain unwind, and all these sites are now available to attract negative anionic particles. Kitazan is pH sensitive and therefore needs to be used in a pH range that are conducive to construction stormwater discharge requirements. When pH is 9 or above, Kitazan will not work, as well as at 8.5. At pH of 10, the molecule becomes severed. And complete flocculation is not accomplished.
Which, Vern, I think that leads into a kind of a follow-up question, what was being asked earlier, and I believe you just illustrated why that's the case. The question says, if ATS works not so well on some CIDH projects, and remember he was talking about high pH, which you're just illustrating there, I'm guessing because of high molecular weight drilling fluid is difficult to remove and thus needs special filter media. What I'm hearing, what you just said, is maybe it just needs pH adjustment.
It's possible pH adjustment will get it, but what we have found when we're dealing with CIDH is usually there is another particular material that breaks down the CIDH polymer better than Kitazan will.
Oh, okay. All right, and I'm sure you're going to be talking here a little bit about what happens when you go with different medias and what the permit requires.
All right. I have heard of Kitazan referred to as a coagulant, flocculate, and flocculent and polymer. Which is it? So Kitazan is a cationic organic polyelectrolyte that is a polymer and behaves like a coagulant and flocculant. Kitazan by itself will start the coagulation process and continue to form larger settleable masses without the addition of an additional flocculant. And then the next question was about that. It says, what's the difference between a coagulant and a flocculant? So a coagulant is a substance that causes particles to clot or bind together. Typically, this is done using a coagulant of opposite charge of the target particle. The flocculant is added to the suspension of coagulated particles to form larger particles that can gravity settle out and be removed in filtration. And does Kitazan work with truck wheel washes? In many cases, yes. However, there are pH limits. So a truck wheel wash from a concrete plant where elevated pH would be expected, Kitazan would not be the best choice. When used on muddy sites where track-out pH is 5 to 8.5, expect very good reaction from Kitazan. Recommended uses might be with a system like the Moby Dick truck wheel wash, with automatic sludge removal, or by battering out sludge after some settling time. So how is coagulant dose determined on any given water sample? So I am going to stop sharing. And everybody can probably see behind me now. Is that, so the coagulant dose is determined in the laboratory and also in the field. In the laboratory, we grab 5 to 10 gallons of actual site water sample, or we produce the simulated stormwater using distilled water and actual site soil samples. We set 6 jars up like these are set up, with one to represent a control sample that does not get any coagulant added. And then we flash mix, and we settle, and we see what the reactions are after 5 minutes. So I will start this, get my chair out of the way. Okay, we're all injected. I'm going to start a stopwatch. I'm running about 1 minute on the flash mix and 30 seconds to settle. And that settling period is just a slow mix. And then after 30 seconds, I'll stop mixing altogether. And now I know you guys can't see it, but I can already see flock forming in the bottoms of these jars as it's spinning. But it'll become a little bit more evident here as I slow this down and stop mixing. I'm going to go right to a slow mix. And I'm going to go about 30 seconds more. And I'm not sure if you can start seeing this flock. A lot of thick particles forming. All right, and I'm stopping it. Okay, and now we'll let this settle for a couple of minutes as it's starting to settle out. But notice this jar right here. Can you, I don't know if you guys can see it, but see how it's lightening up where you can start to see the paddle in the middle already? And I'm going to turn that paddle just slightly. So what's going on here? It shows me that I put in a different dose for each one of these. 50 parts per million, 100, 200, 300, 400, 500. And I'm seeing here at 100 parts per million, I'm getting very good settling going on. What happened down here by putting more product in? I overdosed. I took an anionic problem that we had when we started, a bunch of anionic particles fighting from themselves. I added enough cationic material to now cause a cationic problem, and their settling will not happen. So this could be caused from pH. You'd want to check your pH. It also could be caused from overdosing, and that's where a jar test comes in. And on site, you collect the jar like so. I'm going to get some polymer. I put in 3 drops. That is equal, they're basically 50 milligram drops. They equal approximately 150 parts per million. So I might be slightly overdosed here, but I'm going to give this a shot with my mixing. Not quite as good as the paddle mixer. It's a little harder to mix as well as you can with that. Same thing with a static mixer. It takes a lot of energy to And let's watch this settle out, if it does. And I can start to see settling. That's probably not coming out as good as I would like it to. But we are starting to see some settling going on here. And then field, you would really start these out with one drop at a time and very slowly work yourself up to the best dose. And that's so now look at this jar here, still looks pretty good. But we took another 100 parts per million to do that, which is about 98 gallons of Kitazan at about, what are they paying? They're paying about $15 or so a gallon. So at almost 100 gallons, $1,500 just to get this, when you could go with the 100 parts per million and get better results. Now, I had some other questions with what if my site is contaminated and regulated for other constituents such as metals, hydrocarbons, PFAS, diesel, gas. So sand filters can be multimedia filters. So for example, an iron can be oxidized into precipitate and filtered out using anthracite coal cap placed on top of the sand. There are various carbon materials, clay materials, and other mixtures of these available. Other considerations in granulated activated carbon, aka GAC, is the type being purchased. So acid washed carbon costs more than unwashed carbon. However, to bring pH down to dischargeable levels in the unwashed carbon, recirculating the water through the GAC is necessary to bring pH down. However, the more you do this to the unwashed GAC, the more dissolved oxygen is removed. Therefore, paying more for acid wash GAC is almost 100% of the time the better way to go. With chemicals use involved with stormwater treatment, how do you guarantee no chemicals into the environment? And I am going to share screen again. We use the residual test. And it's essentially a starch iodine test where we have, this would be the filter of what it would look like without any Kitazan, and this shows the presence. It does not determine concentration. This just tells me, is it present or is it not? And with that known, that it comes out like this, we can keep discharging. We check this about every 4 hours as a company. It's required every 8 hours by the permit. And that's that. So, John, do we have any questions that people would like to ask?
At this time, I think I've fielded them all to you. If someone has a question, would like to talk to Vern, feel free to unmute yourself. We can do that right now. Anybody got a question? So Vern, we were talking about that there are other chemicals available for such as the CIDH projects. What determines why we would want? What's the deciding factor of why we want to use an alternate chemical?
Because they have a lot of information that's already been, how do we say, just determined that this is a known product working with this particular material. So most of these that I see coming at me are already well-known chemical reactions.
Okay.
I have a question.
Yes,
Okay.
go ahead.
Let's see. So I work in very remote areas, and I was noticing like all those, kind of semi-trailers and stuff like that to move into an area. And I was wondering, you know, what kind of experience you may have had with putting these systems in perhaps like remote areas on national forests or in the mountains with difficult roads, and how you've kind of maybe worked around problems like that.
Okay, so do you remember the photo that had the oblong ponds in it that I showed? It was a photograph of oblong ponds. Okay, that was a muck pile built up in about an hour and a half outside of Forest Hill. And it was the PG&E surge shaft job that we were on, and we had to correct pH and clean the water. We actually got 40-foot containers down there. We hire very good drivers. They can do that kind of work, and we can get those in places that when I watched the gentleman removing them, I couldn't believe my eyes, how well he did. The traders are so the containers are 40 feet long. They're a big piece of equipment, but the traders and the filters separate, they're only 20 feet long. And we have made systems in the past that were only 12 feet long, but right now I don't have any of those systems in stock.
Thank you.
You're welcome.
All right. All right. If you have a question, go ahead and put that in the chat or unmute yourself. I have a question too while we're waiting for maybe someone else. We're talking about when to use different treatment chemicals. The permit has something to say about it as far as you were showing the starch iodine test. That will determine one route. Well, another route has to be taken if a chemical doesn't have a field test that can produce results within 1 hour. And it's got to go through a battery of fish toxicity testing. Now, that sounds really painful to me, but I know you and I've talked in the past, there's reasons why someone might want to do that. What would be those?
Well, because they could use a much more powerful polymer that does the job more effectively. But the thing you have to have is you need storage. They give you in the permit, they give you the option to submit for testing, and then you can just discharge before you get your results. It doesn't require results, but in my opinion, you're taking a big risk by not waiting for those results from the fish toxicity testing. It's a 96-hour bioassay. It's not a cheap test. And once you've built up a history, you have 2 or 3 of those tests behind you, maybe you could take that risk and submit for future toxicity, but you can't discharge anything that's been treated until after it's been tested.
Right. And it sounds like what's behind all of that are economics, that these more powerful chemicals mean maybe less chemical, perhaps significant cost savings.
There is a polymer that I am trying right now to get legalized in the state of California through the Water Board. It is Kitazan, but it has a polyaluminum chloride benefit to it, and or aluminum chlorohydrate, however you want to look at that. And the polymer uses about half as much as regular Kitazan would. So you can cut down the use, you can cut down the risk by not using so much. There's all of that that's good for it, but we still have to get the approval to use it based on the residual test. Now, there is residual tests for the residual aluminum, and that's what we're trying to get them to approve.
I have another question.
Okay.
Let's see. So the new permit is going to require, I think you said, ATS for pH outside of the 6 to 9 range. Is there, either you or John, do you have an estimate of like how many more like ATS systems are going to be used for the kind of construction that we have seen already? Like, is there going to be a big increase in need for ATS based on this new permit requirement?
What I've noticed over the past few years is we used to get jobs of all sizes, from 200 to 400 gallons a minute up to 3,000 gallons a minute. What we're finding is these smaller jobs have wised up. It is cheaper to button up the site with a good BMPs, upkeep those, than it is to bring in an active treatment system to keep you going through the winter. So where you're going to probably see more of these showing up is, first off, on your larger sites, on your sites that have colloidal clays, long, steep slopes. These kinds of things are as where you're going to start seeing these pop up more. I would not expect them to be seen a lot more than what we used to see, just in different locations where they used to be everywhere. Now they're more in the area where they're going to be used for sure. And traditional BMPs will not control the accelerated release of erosion.
Okay,
All
thank
right.
you.
All right. And Vern, there's a lot of discussion in new permit about passive treatment. Maybe you could speak to that. How is passive treatment different and maybe even similar to active treatment?
Passive treatment's different in the fact that they just take a sock, what I call a sock. It's almost like a piece of the green Filtrex, and they'll fill that with, say, Kitazan, and they'll put that into a waste stream, but it's not running to filtration. It's not running for it. So what I understand so far, and I'm still reading into this new permit, is they're not going to allow cationic polymers in the use of construction controlled stormwater without having some kind of filtration for that.
It's also often added to hydraulic mulches and sprayed on to a surface.
Right.
And so obviously the concern is overdosing, and that's what is toxic to fish life.
And there is, I tell you, I've worked with these socks before, and I've worked with some very poor made ones, and I've worked with some that were better, but there is no real control. So when I found them and used them before, I was letting water flow into tanks and then taking that water that was pre-treated with the socks and run it through filtration.
Yeah. Okay, well, good. Any last questions from anybody? Just checking the chat here. All right, Vern, if people do have questions, okay, here we go. And this question, I knew this would come up. I understand there are many variables, but what's the minimum cost and average cost for utilizing ATS? I probed you with this question.
I had to ask somebody yesterday just to see where we're at right now, because I don't deal with the money a whole lot. However, we talked about what is, let's just say, assume an 800 gallon per minute system for a 6-month time period. You're probably looking at around $100,000 by the time it's paid for the chemical, the rent, operators, so on. It adds up fairly rapidly.
Mm-hmm. And that's why you were saying that to put down a really good hydraulic mulch, you're looking at maybe at top of the line, $7,500 an acre. So if it's a smaller site, you can go a long ways. You could probably have several applications of a really good hydraulic mulch and still be less.
I have watched one site here in Auburn, California, who brought us on 1 year, and they paid dearly for that. The next, excuse me, the site's still not completed, but they buttoned it up from every year after that. And I'm sure that it was maybe 10 acres. It wasn't much at all.
Yeah. And it always boils down to economics in the stormwater world. You know, that is obviously something that we got to pay attention to. Of course, compliance, we want to comply, but the route we go will usually be determined about economics. So Vern, if people have questions or think of questions after this workshop, how can they get a hold of you?
Well, right down here, let me share screen again.
Sure.
So this is Active Treatment Systems, our address and our website. And right now, I understand our website got hacked, so it may show that we're actually, it tells people that we're closed when we're not. But my name, here is my email address and a phone number. I'm going to leave that up there for people to write down, and phone number they can write down if needed.
All right, or take your iPhone out and take a picture of it real quick.
Yeah.
So Vern, I appreciate your time, this presentation, and great as always, good information. Every time I listen to you, I learn something new. So thank you for taking time, and all of you that attended, thank you for being a part of this. We hope you can take advantage of other Stormwater Awareness Week workshops. There's quite a few options coming, plus our keynote videos that the new one just came out today, which features the Carquinez Strait and the executive officer of the San Francisco Bay Regional Water Quality Control Board. So you'll want to check that out. And in that video, we also talk about stormwater treatment systems, and you'll get to view a real one that's working at a real life industrial permittees facility. So thank you for attending. Thank you, Vern. And
You're welcome.
we'll see you at the next workshop.
All right. Thank you.